Hello, everyone, and welcome. Thank you for joining us this afternoon for the panel, The Planet We Have, the Planet We Want. Before we start, I'd like to take a brief moment to express how humbled I am by your loyalty. The support you've given MIT through the Campaign for a Better World has allowed us to amplify our distinctive strengths in education, research, and innovation, and to advance our work on solving some of humanity's most difficult problems. On behalf of the faculty, students, and staff, please accept my sincere thanks for your extraordinary generosity. Now, let's move on to what I anticipate will be a thought-provoking conversation about this era's defining challenge, climate change. It's hard to count the number of ways that MIT is working on climate, but I'd like to draw your attention to two of them. I have the distinct honor of chairing the MIT Climate and Sustainability Consortium, which brings together an alliance of leaders from a broad range of industries. These 16 companies are deeply engaged with us and with each other on vastly accelerating the development and implementation of scalable solutions to address climate change. I would also like to highlight MIT's Climate Grand Challenges, which is mobilizing the Institute's entire research community to tackle the most difficult unsolved climate problems through 5 flagship projects. Today, we have the privilege of hearing from the leaders of 2 of these projects, Professor Noelle Eckley Selin, and the co-chair of MIT's Climate Nucleus, who's co-leading a project that seeks to bring computation to the climate challenge, and Professor Yet-Ming Chiang, a material scientist and serial entrepreneur who's co-leading a project that aims to transform industrial processes through renewable electricity. Rounding out the panel is Associate Professor David Su, an urban and environmental planner whose research focuses on how to use environmental policy and planning to better shape cities. Now, it is my pleasure to turn things over to my esteemed colleague, Professor Ron Prinn, who will be acting as moderator. Ron is the director of the Center for Global Change Science and the Joint Program on the Science and Policy of Global Change. Ron?
Thank you, Anantha. We are at a crossroads in addressing what is arguably the greatest environmental difficulty that has faced the world in recent human history. Dangerous climate change is no longer something that we talk about happening in the future. It's happening today. And I'm going to give you a few examples of that. And it's getting worse, I'm afraid, day by day. The 17 warmest years recorded since 1880, when we had thermometers around the world good enough to do this, the 17 warmest years recorded since 1880 have all occurred in the last 23 years. Each year, the data shows hundreds of regional high-temperature records are being set. And each year, the same year, you get a few or no low-temperature records at regional levels being set. And in most of those 17 warmest years, you had only 1 or 0 low-temperature records. For those of you who think about statistics, and then you know that this is a changing away from a normal distribution in a very, very drastic way and happening so fast. As predicted, data shows that the global atmospheric humidity, which is measured with meteorological balloons every 12 hours around the world, that it's continuously increasing with temperature, as you expect from the Clausius-Clapeyron equation, and thus accelerating the warming. Water vapor is the single most important greenhouse gas, and fueling more and more intense hurricanes and typhoons. It's the fuel of mega storms. As predicted, data shows the poles are warming faster than the equator. That lowers the equator to pole temperature difference, and it's changing the movements of storms and making some of them more destructive. As predicted, data shows Arctic summer sea ice extent is rapidly decreasing. We're thereby replacing a reflector of sunlight in the summer in the Arctic region with a dark surface that absorbs it, the dark surface being very mineral-rich and plankton-rich ocean water. This accelerates the warming of the Arctic even faster. As predicted also, data shows that climate extremes, floods, droughts, wildfires, and heat waves, they're all intensifying. And what we notice with the wildfires and drought in the West are persisting longer and longer and longer. And you know the lake levels of most of the big water reservoirs in the West, the very dire straits that they are in. I could go on with this sort of discussion. But the point here is this is the planet we have, and we shouldn't forget that. It's not a perfect planet. We understand the causes of these damaging climate changes very well. They're centered around what we call radiator forcing rapidly increasing. The problem is that we need to exit from the pathway we are taking right now in the things that influence climate. The solution lies specifically in moving to a new net zero emission greenhouse gas emitting world by the middle part of this century. Now that's only a few decades into the future now. It used to be 5 decades. It's now maybe 2 or 3. Today, I'm not going to talk anymore about the science of the issue or of the things that are happening. Today, we're going to focus on the challenge of achieving this solution of getting to net zero emissions by means that are globally feasible. That means affordable. Equitable, that means everyone gets treated the same. And sustainable. We are not creating additional environmental problems in order to solve one. So let's begin with what can be done in urban areas where most of us live, and certainly a significant fraction of the world population lives in urban areas. Are urban areas part of the problem? We'll see. David, I'm going to ask you, what role do urban areas play in driving global climate change today, and what can be done to transition urban areas around the world from being part of the problem to part of the solution?
So, Ron, thanks. I feel like I always want to start every time I talk to any audience of students or faculty or the public, just saying that at the same time, we all have climate concerns for sure. At the same time, we should also recognize that we are able to shape the future. Lots of things are happening in terms of technology, society, the economy that are going to actually drive us hopefully to a more sustainable transition. And so one of those examples I just want to talk about is urbanization globally. 2007 is when the UN estimates that more than 50% of all humanity started living in cities. If you look at the future projections to 2050, which is where we're concerned about climate change and trying to achieve a net zero energy system, the UN estimates about 66% or 2/3 of all humanity will be living in cities. That's overwhelmingly an increase from where we are now. All that urbanization is mostly going to occur it's already been happening for about 20 years in China, but it's going to happen in sub-Saharan and Eastern Africa. It's also going to happen in India. Those places will essentially go from about 40% urbanization to 60% urbanization. So cities are an important part of the solution. We think they lead to development, higher income, higher levels of education. But I also want to emphasize that it's an important part of the problem. We, I think, have to rethink how we understand cities are part of the problem of consumption. I think I used to be a city official in a couple of large cities in the US, in New York and Seattle, and I always felt there's a certain amount of complacency among urban dwellers, many of which we probably are. We live in cities, we're relatively high income, relatively more educated, and yet we have to recognize that a lot of consumption that occurs in other parts of the US or other parts of the world is linked to our urban lifestyles. And so actually I think it's an important point that we can think about reshaping our cities going forward, but also the cities that haven't been built yet. We can think of what an urban life would look like going forward that is not going to increase our material footprint. And so if you look at all the estimates, there are policies, there are technologies, there are plans to try to lower the material consumption of cities by about 50%. We know we need to lower the consumption of cities by 50% because that's how much renewables we could possibly build in the next 30 or 40 years to try to meet our mid-century goals. But I always try to be hopeful when I talk to students, saying that if we can think about how to lower our material consumption in cities and we work with the trends in technology, then we can try to meet our mid-century goals. But it requires us to rethink how we relate to the countryside, how we think about our urban lifestyles.
Okay, thank you. New technologies are regarded as essential in achieving the transition that we're talking about here. Yet-Ming, I have a question for you. Can electrification of our global energy system and new affordable and sustainable batteries to store energy, electrical energy in that system, be a big part of the solution? And are incentives needed, however, to push us in the right direction there?
Thank you, Ron. So first of all, I want to say, add my welcome to MIT. You've been welcome. I want to say again, welcome. And you notice from what's on the screen that I, too, like many of you, an alum, have been here at MIT. I actually sat in Killian Court as an incoming freshman in 1976. Right? My professional life changed in the mid-90s because I started working on things related initially not to climate, but which became relevant to climate, and that was batteries for electric vehicles. Right? And that's, so Ron is asking me about that. So if you listen to those statistics that Ron mentioned at the beginning, it's easy to be depressed. Right? Climate change is often a depressing thing, but you cannot be a technologist or attempt to develop new technology without being optimistic. Right? And so, in part, I want to say, I am optimistic, but we also have to be realistic. And one of the things that we have to keep in mind is that this is a giant problem, and to address a giant problem, you have to come up with solutions that really are scalable. Okay, so when it comes to batteries, what I used to do, starting in the 90s, was to work on batteries with really exotic and novel chemistries. Right? And so things from parts of the periodic table where the elemental abundance was not great. But we could make these really interesting, cool designer materials. And we thought about making batteries that would use those. And over time, what I came to realize was that that was not going to be scalable. And started working on batteries that use more abundant materials, right? Elements that are very abundant in the Earth's crust. And I've kind of continued that direction. So I'm going to give you a specific example. And so over time, my work on batteries has been a drive to the bottom in terms of cost and abundance. So I'm trying to get to the bottom as fast as I can. Now, that's been my theme over the last decade or so. I happen to have a friend at Georgia Tech who is working on better toilets, part of the Gates Initiative on toilet technology. And I say, Shannon, you've beat me to the bottom. All right, but I'm still trying to get there. So if you ask the question, what is the planet that we have, from a materials point of view, the planet that we have is a big ball of iron, right? And so it turns out that using iron to make batteries is not only feasible, but might be one of the solutions here. So I'm going to tell you about a particular technology. And we came upon this after doing a lot of analysis about what would be scalable and scalable in time to meet this mid-century kind of a goal. Right? So the battery is an iron-air battery. It turns out that if you take iron, it likes to rust. Right? And as it rusts, it oxidizes. And if you build the battery in the right way, you can get those electrons that go towards rusting that battery to go through an external circuit, and then you have a battery. Right? So the iron-air battery, even though we didn't invent the iron-air battery, it's over 50 years old, but we've reinvented it in a way to address storage of electricity that can buffer those many days that you have. For instance, the sun doesn't shine for a number of days, and you look at any location in the U.S. and there are periods where you have outages of renewable electricity for multiple days at a time. Right? And so providing that affordable, very reliable electricity that we all want, if we can have low-cost multi-day storage, we think we can solve that problem. Right? So this iron-air battery that's based on rusting and unrusting. You rust the battery in order to discharge the battery. You unrust the battery to charge it electrically. Right? This device is something that we're developing and started at MIT. We're now developing it at a commercial level in Somerville, Massachusetts, a company called Form Energy, which has about 300 employees right now, trying to grow to 500 within a year or so. And so really trying to scale this. And when you think about the scaling challenge, it goes something like the following. At the MIT Energy Initiative, we're just about to complete a study. In fact, will be launched on Monday, this coming Monday, down in DC, called The Future of Energy Storage. In that kind of work, when we look at, by mid-century, in order to take renewable energy and turn it into this very reliable electricity that we all want, how much do you need in the way of batteries? Well, the round number we come up with is 100 terawatt hours of storage. Now, you and I don't, neither of us lives in terawatt hours on a daily basis. I've tried to put that into perspective. What does that mean, 100 terawatt hour storage? This is globally. Right? It means that if in the year 2050, we imagine that the Earth will have 10 billion inhabitants, for every 10 of us, there'll be a battery that helps provide that reliable electricity, which is about the size of an EV battery pack. Right? Doesn't sound crazy, right? So every 10 of us will share one EV battery pack to provide that reliable electricity. Can this iron-air battery as one option get there? Well, right now, if we look at what it would take for some of the elements that go into batteries, in order to meet that 100 terawatt hour objective by mid-century, you would have to have production of those metals that increases year upon year, compound annual growth rate of some 20% for the next 28 years. Right? So 20% a year for the 28, that's a huge lift. Right? In the case of iron, we're sitting on this giant ball of iron, it only has to be about 2% or less than that. And so we can, in this case, I think, scale it. And so that's an example. That's not the only example. That's an example of possibly a scalable solution to provide reliable electricity that we all want.
Thank you, Yet-Ming. So achieving the needed transition involves understanding complex interactions between the human system and the natural system on our planet. To get the correct answers, we've learned that things we used to study in isolation, to get the right answer, you need to study them in their interactive true state. So my next question is to Noelle. How can we use integrated modeling, analytics, and data to explore proposed solutions in a fundamental way and address their equity and sustainability, the last two being really important for the transition?
Well, thanks, Ron. I think one of the things that you said is, how do we really understand the world? And I'm really struck by Yet-Ming's description of the big ball of iron, because I've never actually heard that one before. So, that's one view of the world. But I sort of start as an earth scientist, and you can think about, well, you might not start with big ball of iron, but you might start with big ball of water or something like that. But in fact, it's not really a big ball of water, it's a big ball of people. And when you think about sort of what determines the processes, the climate of the Earth, the sort of natural resources that we all depend on, humans are really the dominant force and increasingly the dominant force in determining those processes. So if as an earth scientist I want to study those processes, I really need to understand on a sort of fundamental level what's happening with people, what's happening with how people interact with their environment, and hopefully in ways that can kind of guide decision making. Because if I understand sort of the wrong system, if I just look at the environment in isolation and I don't account for human feedbacks, then I'm going to get the wrong answer. You know, my data, my analytics, my modeling is not going to be accurate. And I think we saw some of that interactions in, you know, what to a climate scientist is even kind of a minor way in terms of those interactions, having experienced what happened during the COVID pandemic. Right? You can't really understand COVID as just a sort of pathogen, right? The way it behaved in the environment, in systems, really depended on not only, you know, human behavior, but also institutions, laws, norms, sort of the structure of society, the underlying structure of supply chains that we're still seeing the impacts on now. So if you're going to really understand what happens in a future climate, you really have to understand and better map those interactions. And that's where better integrated models and integrated data come in. And we've been sort of developing those for a couple of decades at MIT. You know, Ron Prinn Center, the Center for Global Change Science and the Joint Program on Science and Policy of Global Change was one of the pioneers in these areas. But as these interactions and sort of their impacts get bigger, we really have to ramp up that work, because some of the science of those interactions, that's some of the most uncertain and frontier science that we can really be looking into here at MIT to really understand that at a systems level. So that in my version of sort of the planet we have is really a human-dominated planet. And when we think about sort of some of the equity questions and the sort of broader issues of well-being questions, that really gets into some of the questions of the planet we want. And one of the first things I said when I saw the title of this session was, okay, so who's we, right? We in this room. The planet that we have, the planet that, you know, we control the resources of, the types of resources that we can mobilize for our own well-being is very different when we're sitting here at MIT than other places in the world. And our priorities might well be different from others in different situations and of future generations in particular who will inherit the climate changed world. So how do we think better about sort of the analytics that go into that and really understand what metrics are going in the right direction or not? And as we think about sort of that question of the planet we want, you know, climate is certainly necessary for sort of the kind of action that will get us to net zero is certainly necessary for that, but it's not sufficient. It's not the only metric. None of us experience just global average temperature, and if we experience a good global average temperature, everything's fine, right? You know, so we really have to think about this as a broader sustainability challenge and think about how our climate action intersects with these other sustainability goals and other human well-being goals. And to go back to the magnitude of that challenge, the COVID example, we saw CO2 emissions go down 5 or 6% during 2020. And pretty much everyone realized what was happening there, and you could see the impact that had on some of the economic activity, traffic, other things, 5 or 6%. We're talking about getting to zero. And we want to get to zero in a way that doesn't have those big impacts that 5 or 6% have. That's a big challenge, but that's the kind of challenge that we're aiming towards and developing tools and technologies to get us there.
Thank you, Noelle. So we have time for a little second round, so I've got some follow-on questions for the panel members. Let's begin again with David. David, my follow-on to you is, what incentives and policies will accelerate this urban transition that you're talking about, and how may that differ in Mumbai or versus London and Rio de Janeiro and so on? Will the same incentives work, and will the same policies work all around the world, because only one city does all of this really good things. We haven't achieved what we need.
Well, I think this gets to the point that Noelle made about what an equitable or just transition is going to look like. We know that you have tremendous inequities in cities like Rio de Janeiro and Mumbai. We know that there's extremely rich people and extremely poor people in those cities, but those cities tend to be what we call, developing countries, and those countries will need to develop for various reasons to have a higher quality of life and a higher standard of living. At the same time, I think we have to rethink how actually, have become maybe more focused on, I'm from Massachusetts, and actually more focusing on policy in Massachusetts, the United States in the last few years, after having done work in India and Sub-Saharan Africa and other places. If only because I think that those places will have to develop, but it's really hard to talk to policymakers or residents or citizens of those places without actually addressing the fact that our material consumption is still in multiples. Our average consumption in the US is about 10 times what average Indian citizen emits in terms of greenhouse gas emissions. And so those places have really nowhere to go but up, but we also know for a sustainable future, we have nowhere to go but down. And I don't think we should talk about down as a decrease in our material standard of living. We know that we have good examples of economies that have managed to decouple economic growth and their material consumption or their greenhouse gas emissions. California is probably the most famous example, 6th largest economy in the world, has had relatively flat electricity consumption for many years, and GDP growth, of course, has been rather robust in California. So we need more examples of subnational governments, cities, states that can do that. And if we can show that the 6th largest economy in the world can do it in California, then developing countries will actually have I think we'll actually regain, honestly, some moral right to talk about what a development path should look like. And I think that would actually provide a useful guideline, not even for developing countries, but for other developing states. Massachusetts, California, and New York learn from each other. But we also know that we have lots of inequality problems in Massachusetts, California, New York that we need to address. We need to address those problems to have the moral right to talk about what a future development pathway is going to look like.
So the answer appears to be that it's going to be a lot of bottom-up, if I can use that term, in these cities, rather than a global overarching policy.
Well, I think I always have two rationales for looking at things from the bottom-up perspective. I'm an urban planner, so my scale of, unlike Yet-Ming's argument about scaling up, which I completely agree with, but I also do think we need local action as a way to use as laboratories for experimentation. We know the energy transition is going to be big enough and is pervasive enough that we're going to need different solutions in different places. We need local governments and subnational governments as realms for experimentation. And the other argument is this kind of heterogeneity. We're going to need a lot of different solutions to achieve a broad-based energy transition. Those are my arguments for bottom-up action. But I always say bottom-up action is a complement to things that happen at industrial or global or technological scales. One area that Noelle and I have talked about a lot is air quality. And I think there's a kind of local argument, it seems like there's a very robust literature now showing that people really care about their local environment and air pollution. And we know that there's incredible health impacts of the fossil fuel system that we have. And so if we were to decarbonize that system, we would actually realize so many fewer deaths and so much less loss of human capital in cities, even in the US, that we could pay for decarbonization 2 or 3 times over. You look at a country like India that has, I think, 13 of the 20 most polluted cities in the world because of mostly different sources of air pollution, local, global, national. But if you look at what the impact for human development would be in India, if you could actually help them decarbonize as part of their development path, rather than going through the whole cycle of a fossil fuel system and then decarbonizing, there would be tremendous local impacts. And I think as a motivation, people are very motivated to take care of their local environment. And so actually, Noelle and I have talked a lot about research recently. I'm doing new research in air quality in buildings and in cities, if only because I think people are more motivated to take care of their local environment than they are a far off global future. Having said that, I always say they're not at all contradictory. a local decarbonized environment is going to be a much better, higher quality environment for people to live in and will reap huge benefits in terms of human capital. So.
Okay, thank you, David. That's a wonderful example that David and Noelle are going to be working together. They're totally different departments and backgrounds, and you see the synergy. This is MIT. I've been here for 51 years, and I love it, the fact that you can work across many boundaries. They really don't exist. Yet-Ming, my follow-on question for you is, you've talked very eloquently about the energy system. What else could we electrify besides energy? And what impact would that have? So what else are we doing wrong, and how can this solve it?
Yeah, you know, I realized, Ron, I never answered the last part of your first question, so I'm going to come back. You asked about incentives, and it really touches on this issue of policy. Right? So I did want to, before I turn to that second question, I wanted to say that, you know, I view the role of technology development as providing alternatives so that policy can be made. You know, if you look at the history of electric vehicles in this country, you know, there were incentives, of course, right? But they're only incentives because you could imagine such a thing as an electric vehicle. In the absence of technological alternatives, policies are difficult to put in place. Right? And so that's how I think what we do ties into these things. And I totally agree, it's very much local. And I'm going to give you an example of how it happens on a local scale. You know, I have electricity on the brain. I think about electricity a lot. And one of the things about electricity is that this idea that we all have to do with less energy, I don't think is true. You know, we can actually continue to use as much and even more energy if we figure out how to effectively decarbonize it. And right now, the best way to do that seems to be electrically. Right? I talked about how we can store that electricity so that we get it reliably. But in a world of low-cost, widely abundant electricity, there are other things that we can do with it, which is Ron's second question to me. You know, if you look at a lot of the large-scale technologies that enabled the Industrial Revolution, and more specifically the Second Industrial Revolution, and that enables society the way that we have it today, a lot of those great inventions were all based on fossil fuels. And in particular, I'm thinking of cement, right, which the invention of Portland cement is what allowed rapid construction. Right? This building could not have been built without the invention of Portland cement. Steel, this building doesn't exist without steel making. Right? So those two, and then also ammonia for fertilizer, and then later on ethylene for plastics. It turns out that just those four industries contribute altogether about 15% of all the CO2 emissions that our society produces. Right? So 15%, and just cement is 8% of that. Right? So can I take something out of my bag here?
Sure.
I'm going to get down off my chair if you allow me. And I want to show you something that is a representative of something that we're working on here. You all recognize that as a beaver. Right? The engineering animal does its best work at night. This is a cement beaver. Right? And you know, we make this as an emblem of what we're working on and an objective, which is to decarbonize the making of cement. Now, cement's a fascinating material. It sells for 12.5 cents a kilogram, right? Far less than bottled water. Right? It's produced some 4 billion tons a year. Right? And the key number to remember is that each kilogram of cement, this is a little less than a kilogram, the normal making of it produces and releases a kilogram of CO2. That's why it's such a big problem. Right? And so we've been working under the MIT, the Climate Grand Challenges, which you've heard about and which there's a display on the hallway, about how to take this material and decarbonize it. And so this is an early example of a type of cement which I would say is roughly 80% decarbonized. Right? And we haven't gone through the process of figuring out how to scale it all, and I earlier talked about scale. But this is the kind of thing that needs to be done. And the path to doing this, at least the way we're doing it, is using electricity. Instead of burning coal in order to produce that cement through a high temperature process, we're using electricity in an electrochemical process to make it at room temperature, ambient temperature. So this beaver never saw 1500 degrees C. If it was made out of Portland cement, that would not be true. Right? And so this is one of the things that we're trying to electrify, and through electrification, decarbonize.
Thank you, Yet-Ming. My follow-on question for Noelle is, how are the results of these integrated studies that you've been eloquently telling us about, how are they communicated to policymakers around the world? And again, how different are the strategies for looking at developing countries and developed countries, and equatorial versus mid-latitude countries and so on, different weather systems, etc.?
Yeah, I think that's a really important question, and I want to sort of start by saying, it's not just the results of those studies that are communicated. We really make an effort to try to understand what policymakers' needs are in the construction and in the running and the development of those models, because we're not really asking the right questions unless we're truly engaged with those who are going to be using this information. So this is also related to the grand challenge which I co-lead, which is about sort of getting a new generation of climate modeling, but making those climate models more useful and relevant to people around the world. So the solutions, as David picked up on, are going to be very different in different places. And you really need the kind of information that's tied to your local environment. And you're not going to get that from kind of a one-size-fits-all analysis, right? You're going to need analyses that are targeted to the questions that you're interested in at the scales that you're interested in. So a lot of the kind of modeling and analyses we have are highly aggregated right now, but policymakers and decision makers are really interested in finding out what's happening in their backyards, and that's a science challenge, that's an engineering challenge to get them the information, and it's probabilistic information that we need, right? What are the chances that this is going to happen, and how are human feedbacks going to affect what they're seeing in the environment? So that's part of that challenge, but that's also part of the ways in which modeling and sort of the development of this of new technology really is closely coupled with policy and with decision making. And I would say that I think there was there's no policy without technology, but there's no technology without policy either. It's really a two-way arrow. And I direct the Technology and Policy program, which is our 2-year master's program at the intersection of technology and policy. And we really train students here at MIT to understand what goes into developing information and technology such that it can be used. And you really need that engagement with stakeholders, with users, because if you think about it sort of as an engineering design problem, you're not going to design something without looking at the use cases and doing sort of integrated analysis and thinking about iterating with your users and refining your design. Same thing for the kinds of climate information that decision makers are using. So really sort of approaching that as a science and engineering problem really requires that consultation and that engagement, even before the ultimate communication.
Thank you, Noelle. At this point, I'm going to later on ask each of you to give your closing remarks at the end of a few minutes, just changing the framework a little bit than what we designed, because there's some interesting questions from the audience that we should pay attention to. First one is, given how much inertia there is in atmospheric greenhouse gases, why isn't there any thought to circumvent the greenhouse effect to directly vent heat to space, much like hurricanes do? Anyone want to tackle that one?
That sounds like
We're all looking at each other.
I will try to tackle it. This subject is generally called geoengineering or climate engineering. Yeah. By the way, the last thing we want is to use hurricanes to vent heat to space. We are doing that. They're getting more and more intense, and yes, they're venting to space. But I'm afraid the damage they do is so horrendous that we don't want to use that as an approach or anything to make automatic ones. The issues with geoengineering, and we've done a number of seminars here at MIT and jointly with Harvard on this geoengineering. One of them is that we can not vent more energy to space, but that we reflect away sunlight that would otherwise come down and heat the world up. And whenever people dream up these things, there tend to be unintended consequences or ignored consequences. So the whole business of putting particles in the high atmosphere, in the stratosphere, was born when we had Mount Pinatubo in the previous century. And that cooled the world by about a degree centigrade, or more than almost a couple of degrees Fahrenheit, and for a number of years, and then all of the particles slowly fell out. And now we looked at it and it said, well, these people who think about these things said, why don't we have aircraft going backwards and forwards, putting particles into the high atmosphere, and you know, that's what we give a legacy, of course, to our children. We continue to use greenhouse gases and fossil fuels because we could grow and grow, and we just put more and more particles in the high atmosphere to give less and less sunlight. So what are unintended consequences there? The first one was discovered by the Pinatubo phenomenon, is that global yield of food went down by about 5%. And that is because rainfall in itself, you know, we couldn't measure it globally to great accuracy, but you know that what drives rainfall is evaporation. And evaporation, we all know this, is sunlight. You have a sunny day and the water disappears off the pavement a lot quicker than when it's not. It's a cloudy day. Part of it is to do with humidity. So yields, you know, sunlight drives photosynthesis. That drives the production of food globally. We do not want to interfere with that. Unintended consequence, number one. Number two, people began to think, we have an ozone layer up there. And guess what? Particulates, just as was discovered in the Antarctic ozone hole, they have ways in which they destroy ozone, just simply having catalytic surfaces, for example. A terrible unintended consequence. So it's a dangerous business, but scientists like myself think we should continue to think about it in case everyone ignores what this panel is talking about up here, about the solutions, and we continue on our merry way along the pathway that we are going. But let's tread carefully, very, very carefully when it comes to geoengineering. If decarbonization will create more economic benefit than costs, and this I'm going to ask from Yet-Ming, for example, why is it so difficult to sell politically? How do we convince the US and other countries that energy independence does not mean fossil fuel independence? That was the question.
Okay, I'm trying to understand the question.
Yeah, it's a trick question. I don't know if it's deliberate.
Yeah, why is it so hard to sell? Well, you know, I don't know because I'm not a political scientist. But I will tell you that at least when it comes to the US, one of the experiences I had back in the 2000s when I'll tell you, that was when electric vehicles first started to be taken seriously. So you might remember that right around 2000 was when the first Toyota Prius came out. Right? Question right then that was, why would anyone ever want a hybrid car? You know, why would you ever want a car with 2 drivetrains in it when you could have one with just one? Right? And so, of course, that question seems kind of silly today. Why would anyone ask that question? Is the question you'd ask today, right? And so what happened then shortly after was that then the all-electric vehicle became the debate. And why would anyone want an all-electric vehicle? But I'll tell you, in relation to this, how hard is it to get through? One of the experiences I had then was that we had a company then that built in the U.S. the first electric vehicle batteries here in the U.S. Right? And what we observed was that as the electric vehicle industry started to grow around the world, we were the only country in which there was no political will or mandate for our car companies to use a battery made in the US. Yeah. Okay. Every other country developing a electric vehicle, most of them in Asia, they all strictly used batteries that were made in their home country, not in the US. Right? And now, that actually, I feel that that really slowed down our electric vehicle industrial development. Didn't help the company that we had at the time either, right? But I think, I'm hoping that this time around, it's going to be a little bit different. That that there will be more support here in the U.S., and part of it has to do with things such as, scarce and rare minerals, rare earths, not only rare earths, lithium, cobalt, nickel, things like that. That if you look at the world map of where they're sourced today, very little of it is sourced in the U.S., and that's an aspect of kind of political will that I hope we can take a different approach to.
Yeah, a lot of people think there are all these low-hanging fruit that are there, ready to pick and so on, and there is this inertia, it seems, in human behavior before they see and grasp. Do you want to add something, yes. David and well, Noelle, go ahead.
I think that shows the limitation of looking at this just as an aggregate economic problem. I mean, I think we know that people make decisions for all sorts of reasons, and one of which is distribution of benefits. And if you think about sort of who is benefiting, that determines a lot of the politics of issues. But also, there is inertia, and there are real challenges as to thinking about what kind of sort of aggregate policies we can get done in the political system we have, right? So framing the problem just as, well, anything that we would agree that the benefits outweigh the costs, and of course we should do it, that if we think about this as a politics problem, well, why don't people always act based on their rational economic interest, right? If that's the case, you would buy the cheapest car possible all the time, right? Other things matter, right? Other objectives matter, and other objectives matter in politics. And one of the other things that matters is how power is distributed. And that's really important in determining outcomes, and our political science colleagues certainly remind us of that in terms of thinking about why decisions are made.
Let me just tack on to that, because I think, I would maybe just add to what Yet-Ming and Noelle said, which is I would actually disagree with a little bit the premise of the question, that we are so hindered by inertia that things aren't happening. Last year, 70 or 80% of our capacity additions to the electric grid were solar and wind. Solar and wind are now so cheap that you can build a new solar wind plant more cheaply than you can continue to operate any existing fossil fuel plant. So you could just actually decommission your coal-fired power plant, you could decommission your natural gas plant, and replace it with a cheaper solar and wind plant. Now that comes with challenges on the electric grid, which Yet-Ming has talked about ways to solve. But just to give you an example, to add on to what Noelle said about political will, I'll just give you a kind of anecdotal example, but actually I think it's quite representative of how we think about social norms are going to change. I rode here on an electric bike. I love bicycling, but it's a hot day outside, and I rode an electric bike that's not any more expensive than a regular bike. I saw one of my colleagues last week who I hadn't really seen in person for about 2 years. And he studies some aspects of environmental policy, but he's not really an environmental policy person. And just in the conversation catching up after 2 years, he told me he bought an electric car. And I could not get him to stop talking about his electric car. It was great. Like, here's somebody who don't think about as, deeply environmentally motivated. But he was so thrilled by how much better this technology was. And he said that it was actually an engaging thing. This is kind of this weird phenomenon where I got solar panels and I actually check my solar output on a regular basis. And I know lots of engineers and scientists who do that. But our neighbors check this. And I think there's kind of this social diffusion aspects of, we know the technologies that are coming are so much better, so much more pleasant, so much cleaner, so much more efficient. We actually have a runway for the next 10 years. We know exactly what we have to do. We have all the technology we need to do it. I think at MIT we tend to focus on problems that are further out. We like focusing on harder problems. We actually know what the runway is for the next 10 years. I think when you talk about inertia to do the really challenging things, those are kind of like inertial problems for like the last 20%. We know what we have to do for the first 80%, and we actually have all the tools. Now, the implementation problem, I think, is challenging because, as Noelle points out, in aggregate or local solutions, I strongly believe that, if you live in the upper Midwest and you live in a relatively low population density place and your average driving is, let's say, 200 miles a day, you're just going to need a different electric car than if you live in a city and you drive once a week. But at the same time, I think all those technologies are there, and there's really compelling ways to do this in these different places. Large parts of the Southwest, upper Midwest could be energy exporters. They have almost no problems with renewable siting. They could be sending solar and wind power to the rest of the US quite easily, and that's true for a lot of places in the world. So I actually feel very hopeful. So I think I just want to disagree with this disembodied person slightly, that I think I'm very hopeful that we know what to do, and I think it's not hard to sell. Those things are actually cheaper already. So,
Okay, let me go quickly to, it's really asking about coordination between the various activities going on at MIT. One of them asks the coordination between the centers I'm involved in and others at MIT, such as the Mobility Initiative, the Climate and Sustainability Consortium, and so on. The bottom line is that there is a significant coordination between all of these. The Mobility Initiative part, of course, the MIT Energy Initiative, the Global Change Joint Program, has been a partner of the Energy Initiative. We, of course, look to the initiative to understand technologies and costs, and we then put them in the integrated system modeling that we do to ask, which are the least cost ways of achieving various climate objectives. So it's a two-way street, and we contribute to the various future of series that, and mobility is just one of many of those.
I can talk about that at the institute level as well. So I co-chair the Climate Nucleus, which is the implementation arm of MIT's overarching decadal climate change plan. So if you haven't seen the Fast Forward plan, I would really encourage you to look at that. It's basically the whole of institute effort to try to coordinate all of these diverse labs and centers that are doing climate type work across all of the ways that MIT has an impact on climate. So not just on, our own carbon footprint, although that's a particularly important part of that, but also on education, on policy, and on innovation. And really thinking about the climate grand challenges are a piece of the Fast Forward plan. And the role of the Climate Nucleus is, which I co-chair with Professor Ann White, who's the head of nuclear science and engineering, is to really integrate and make the whole of MIT's climate actions more than the sum of its parts. The Climate Nucleus consists of the leaders of departments, labs, and centers that have significant responsibilities under the plan. And we've set up working groups that try to draw from people across MIT, students, faculty, staff, postdocs, everyone who really wants to be involved has a way to contribute to some of MIT's climate action. And I think this reflects really the magnitude of the climate challenge, that it really is a whole of institute effort. It's a whole world effort. Our world will be different because of climate change, and of course MIT as an institute will be different because of climate change. And it's really the Fast Forward effort that tries to do that in a very explicit way.
Okay, thank you. There was another related question to do with MIT's interactions with other countries around the world. All I can say is it's intensive. but without giving details. So we're coming to the end of this panel discussion, and I want to just wrap it up. First, I want to thank the speakers on this panel. You've done a wonderful job, and I hope the audience agrees with me. I want to thank the participating audience. Thanks for coming along. You're curious. I hope some of your curiosity has been satisfied and that you've had answers. And I'd also like to thank the organizers. I get involved in quite a few of things like this, and the organization of them is complex and very difficult. So Courtney Huff and your various colleagues in the resource development, thank you very much for putting it all together. So with that, I'd like to just close and again thank everyone involved.
Thank you.